by Hodge theory on G mod B. On a flag variety, you have some complex flag variety, there's some Hodge theory you can do there. And if you understand that sufficiently well, then you understand the unitary representation. There's a precise theorem to this effect. And this was the thing that we proved was really conjectured by Kari and Wilfried Schmidt some time ago now. Okay, so let me say what I've got to give you a little provisional plan of these talks. Provisional because it depends how I go through time and so on. So today I'm just going to try to explain kind of what was kind of already known before we started doing this. Sort of relevant to what we've done. And a sort of statement of this main theorem, maybe slightly more precisely than this. Tomorrow, I'm going to try to say something about this Hodge theory business. So, spend a bit of time on mixed Hodge modules and how this interacts with valence and Bernstein localization, which is sort of the key to how this all works. And then Thursday, I'll say something about the proof of the theorem. Some sort of sketch will appear on the board, hopefully. Okay. So now let me sort of move back from all this sort of highfalutin mixed Hodge stuff, and just come back to the sort of basic question of what does the set of unitary representation look like in sort of examples, and yeah, what sort of Lie groups are we interested in, sort of thing. So we're sort of interested in this particular class of Lie groups, which in some sense are the kind of the most interesting ones. So a real group or real reductive group so it's a Lie group which arises as some real form of a complex reductive group. So this is, at least this is the definition that I'll take for this. So I take a complex, so G is some complex reductive group, which we all know and love. And then I take some real form of it. So you can think of that, if you like, as some kind of Galois action, or another way, some sort of some anti-holomorphic involution of this thing, which is supposed to be complex conjugation with respect to this real structure. And so then the Lie group we're interested in is the sort of Lie group of real points of that algebraic thing. Okay. I should say this is the most restrictive version of this definition. There are variants of Lie groups that are near to this.
So you are just using this for the purpose of exposition. You can deal with groups like, say, finite power of SOTY.
That's a good question. So in the papers that we've written so far, we're restricted to this case. Most of the techniques are general geometric theorems, so they work perfectly well for any kind of anything like this, like finite powers. There are a few steps in the proof of this theorem where we really kind of get in and have to analyze the structure of the representations, and there we've done it so far in this case. But I fully expect it's probably not much more work to get from here to the next bit. All the kind of big technical Hodge things are just general stuff. So general stuff about flag varieties, which is always the same.
Excuse me.
Yes.
Would you mind moving the camera to the right side a little bit?
Sorry. Thank you.
Oh, thank you.
And also just a remark for the students amongst us, that if you take something like SL2R, then exactly as Dragan said, if you take a finite cover of this is something that we'd like to call maybe a real reductive group, but this is not of this form. It's a nice little.
another example, another non, this is, so I'll give a couple of examples. Let me give a non-example. So this is a more sort of silly non-example than the more sophisticated one. So if I take, well, maybe let me say the non-example when I say the example. It sits next to an example. So let me take my, so let's take some examples. So I'll take my favorite reductive groups and start looking at their real forms. So the first example of a reductive group that maybe you meet is a torus or C star even. Let's take G to be just the multiplicative group. That's reductive. And so then real forms, you can just kind of classify what they could possibly be. And so the options, turns out there's two options for this one, up to conjugation. Well, it's a billion, sorry, not even up to conjugation, just two things. You can take the unitary U1, so the circle group, there's a real form of this. Or you can take R cross, that's also a real form. So so R cross is an example. A non-example is R plus. The positive real numbers is also not of this form. Those I think are relatively more maybe easier to connect to these ones than the ones which are covered. But so far we're really just talking about these. Okay. Let me give you the unitary duals. So this is a nice kind of warm-up exercise. So, by the way, this set of irreducible unitary representations is called the unitary dual. I'll probably use those words a few times. So, unitary duals. So this one, you probably have done this example at some point in your labs. So the unitary representations are indexed by Z. And so if I have an integer here, I can associate some character. Z goes to Z to the n of U1. That's a unitary representation, and that's exercise, that's all of them. For R cross, it's a little bit more, it's a little bit different. Maybe more complicated is the wrong word. So what do I have to do? So again, it's commutative. So the irreducibles are going to be just one-dimensional. This is figure 1. So for R cross, the characters are going to be one of two forms. So I'm either going to map Z in R cross to something like this, mod Z to the lambda. The lambda is a complex number. So that's a perfectly good figure. Yeah. So I can do this. Z to mod Z to the lambda. So that makes perfect sense for any complex number, since these are real. Or the other option, so you realize it's disconnected. So there's some other option that looks like I can take Z to the sine of Z times mod Z to the lambda. And that's also a perfectly good character. So these are all the characters. And so these are unitary. So the sine thing doesn't really have any bearing. The unitary, if and only if lambda is imaginary. Okay, so you just get sort of two copies of the imaginary real axis.
So what's different in this situation to the high dimensional case? You said you're comparing imperative forces in dimensional.
So faithful. I said the word faithful representations. So when you have this as imaginary, this is actually, so let's ignore the sign one, let's do this one. Or maybe better, just look at the identity component. Then this is imaginary, this is an exponential function. And so it's actually got a kernel, which is the integers. So you're getting really a character of the circle again, but now you have a quotient of this.
If you look at it as a 2R and it's finite dimensional representations, it's an easy linear algebra exercise to show that unitary inner products exist only on trivial representation. This is basically two rows.
Yep.
And this is this Eagle von Neumann theorem, precisely what it says.
So that's a good warm up to my next example, which is
And
here.
just the canonical comment is that
Yep.
these are the things that appear in the Fourier transform on the circle and on.
Yes, this is true. This is a good canonical comment. Yes, exactly. So when you do the Fourier transform for periodic functions, so you sort of reverse Fourier series, you get sort of integer indexed sum, so you get sort of just some series in say z to the n. Thinking of z as maybe e to the 2 pi I theta or something. Whereas on here, if you do just a Fourier transform for a function on R, you get exactly these sorts of, you have a continuous parameter. Okay.
Is there a topological structure of unitary tools that like gets that in general? Like
There
Yes.
is, yes. Yeah, is the what is the word? Bell topology?
Topology, or I mean, it's like Jacobs of topology in primitive algebra or algebraic geometry, and how kernel topology itself to call it.
Yeah, of course, in practice for these, at least these sorts of real reductive groups, the unitary deal is always kind of look like this. There's some sort of unions of polytopes. So it's kind of obvious what the topology has to be. Well, maybe there's something about gluing them together.
But then it's non-Hauser from this points.
Yes. Yes.
And the representation breaks.
Okay. So let me, these are good discussions and questions, so please keep them going. But yes, so the next example I wanted to do was, well, so if I take SL2, again, there's two real forms. There's a compact one, SU2, which I'll just ignore because we sort of understand it. Or the other one is SL2R, or sometimes it's convenient to think of this as SU11. So a unitary group for an indefinite signature. That's how that's formed. So these are kind of conjugate subgroups of SL2. Okay, so let me not do that one. Let me do this one. Okay. So how do you build? What actually do representations of this thing look like? So, and maybe it's not obvious when you first stare at it. I mean, of course, you have some finite dimensional ones, just like from SL2C. But as I sort of pointed out, I'm asserting that the interesting ones are infinite dimensional. So the first example that maybe you come up with, if you think about it for a while, are these ones principal series representations. So this is sort of a general kind of construction you can do for productive groups over sort of any kind of local field, maybe. So we take BR inside SL2R to be my favorite Borel, which is lower triangular matrices. So this inside SL2R. So then this subgroup, so it surjects onto R cross. So for just to fix signs and so on, let me make the map that. So that map, so it just takes the top left entry. And so what I can do is I can take any character of R cross, which I worked out here, and then that gives me a character of B. So if I have a character of R cross, gives me a character from B. And then I can try and induce this up. So GR is plus SL2 in this case. So I can induce this. So this induction, this is sort of a game that you always play in representation theory. If you don't know how to build a representation of something, find a subgroup for which you do, and then induce. So if I write down this induction explicitly, this is complex valued functions on SL2 such that, well, for some convention of signs, I have this kind of scaling property under the B action. Okay. So let me highlight. So this is a representation. Okay. So let me just highlight some features of this, which are sort of typical of the theory, give you a sort of flavor for what things look like. your features. So one thing that you'll note is these parameters. So it's parameterized by some characters of R cross, which, as we saw, has some sort of discrete thing, whether I put this sign in or not, and some continuous thing, which is this lambda. And so the parameters, that's always the case somehow for these representations. So there's some mix of some finite amount of discrete, well, maybe finite is the wrong word, some discrete information and some continuous thing. And the other thing you maybe notice about where this character came from is really coming from a torus, a maximal torus inside his group. And in fact, in some sense, this is always the case again, coming from a torus in GR. The other thing you might notice is that I gave a really sloppy definition of this space. So the definition is kind of ambiguous. So why is it ambiguous? Because I really didn't mean all functions. I want some topological vector space with a nice topology and a continuous action. So I need to pick some nice class of functions and talk about those functions. And there are many classes of nice functions out there. I can take smooth functions, continuous functions, L2 functions. These are all good things to take. And so each of those gives you a different version of this module. So I want to finish my essay explaining what the unitary representations of this are. So I'm going to ignore this for the moment, but I will come back to it. So from here, you can actually kind of build all the representations for SL2 up, it turns out. So let me just introduce some notation for the purpose of this example. So let me write chi lambda. These are just going to be notations for my chi's. So plus is going to mean I don't put the sign in. And I'm going to sneakily put a -1 next to the lambda. And then minus is going to mean I do put the sign. Okay. So here is a fact about these principal series modules that I won't prove. So if you look at the composition factors of this one of either of these things at lambda, these are the same composition factors as for the same thing at minus lambda. And that's why I put the -1 in so that that statement's true. So I'm just going to just focus on, say, the real part bigger than 0, so I don't kind of double up my representations. Okay. Well, I need to allow 0 over there as well. So here are some more facts. So it turns out when you kind of study these things, which you can sort of do, I think this is an exercise you can kind of just do by hand. You like? So this thing is irreducible unless this parameter that I took is an odd integer. So that's how it kind of works out. So there I found some irreducible representations, and I'll get to unitarity in a moment. So if it is an odd integer, so if lambda is in 2z plus 1, then you have some exact sequence. So the thing that you'll notice is under this odd thing, if you kind of do this example, if you do this, is you'll notice you have a copy of a finite dimensional representation sitting inside here, just coming by the Borel-Weber construction. So this looked, if I had C everywhere and I said that this F is holomorphic, I'm just getting this Borel-Weber picture of a finite dimensional representation, algebraic representations of SL2C. And so if lambda is an integer, you sort of have this sitting inside these kind of polynomial things. And so this happens. And then what's left is two other modules. So what's left over turns out to be a direct sum of two irreducibles. which are called discrete series modules. Okay, and yeah, exercise, think about what
But
that,
there's no lambda in the discrete series.
sorry, that should have been a lambda. I'm probably looking at the wrong line of my notes. So now, let me do, so that's what happens for reducibility, at least with this thing. So there's a kind of parallel story, which I'll kind of brush over maybe for this one. So the negative one, this thing, it turns out is irreducible for the same kind of arguments, unless lambda is even. So if lambda is even and positive, you just get exactly the same story as this. So you get a copy of the, let's just say it is V lambda, although we'll never define it again. This is the representation of dimension lambda. Way of index things. So when lambda is zero, so when lambda is even and positive, you get exactly the same thing. No, it's exactly the same notation. So I won't write it again. When lambda is zero, this V0 is the zero-dimensional representation. So that's actually just zero, and then this, the same kind of exact sequence works. This just becomes reducible. So this is just some sum of two things which I'll kind of abusively also give the name ds, although these are strictly speaking not discrete series anymore. They have this name limits of discrete series. So discrete series has some technical meaning to do with how they appear inside the representation given by L2 functions on the group. These don't appear in the same way as the other ones, but they kind of clearly belong in the same family, so they're called limits of discrete series. They're kind of a limiting case. Okay, and then otherwise, you have the same picture as before. Okay, so now we've met all of the irreducible representations of SL2R. They're all somewhere in this picture. And so the unitary representations. I wanted to write down at least sort of one interesting unitary dual. So this is it. So I have these principal series modules, either of them are unitary always if lambda is imaginary. Okay, and I guess lambda and minus lambda are actually the same module, so you may as well take it to be positive if you like. These so if lambda is, so the other option, so it turns out if lambda is neither real nor imaginary, these don't carry any invariant Hermitian form, so they're definitely not unitary. If it's real or imaginary, then they do, and then you can try and figure out if it's positive definite or negative definite. So imaginary turns out to be easy, so it's just all imaginary values are good. Real turns out to be slightly more complicated. So this positive one is unitary if lambda is real and between 0 and 1, because at 1 it becomes reducible. And then the other one, so is you get to go up to 2. Sort of really the first reducibility point kills unitarity. And then all the discrete series are unitary. And all the finite dimensional, well, none of the finite dimensional ones except the trivial representation. Okay, and that's the list.
How do we know that this is a playlist?
Good question. So maybe what I'm about, I mean, there's probably some classical way of doing it.
By hand.
Well, yes, this is it, which is what I'm about to explain. That's good. That's a good thing. So yes, so actually, there's a very good question. So how do you determine this complete list? Well, first you need to get a handle on what are representations of this Lie group? What do they really look like? As we saw, there's kind of an issue about function spaces that's going on, which makes things kind of painful. And And then once you kind of know what they all are, maybe for SL2R, it's that you can just write them down and analyze their structure and compute invariant Hermitian forms and check when they're positive. And that's how you do it. So let me start that process.
Find this in, say, Lang's book or SL2R, but this is very misleading because it works for SL2R if you try to generalize no way.
Yeah. I mean, exactly. I mean, in a sense, yeah, it's just SL2R is just so easy. You can just write everything down. You can just check it. I mean, in a sense, that's what this algorithm does, just in a much more sophisticated way. It just writes down representations, computes signatures, and then eventually by you can bound things and show that you found all the unitary things. But yes, this is a deceptively easy example. And generally, this is much harder. So, all right. So, 20 minutes left, which is great. Thank you, Julie, for the reminder to write video. Okay. So now let me try and say something at least about Harish-Chandra modules. So this is sort of coming back to the point that I deferred about how you deal with these function space issues. So,
Google, can I just interrupt with a comment? Just based on, like, just a little bit of motivation for this is that we know, for example, Peter Weil theorem, which tells you that functions on a compact Lie group can be beautifully explained in terms of the representation theory of the compact Lie group. And somehow, like, a lot of this is motivated by trying to analyze functions on SL2R. There's many problems in mathematics that lead to understanding functions on SL2R. And so, in some sense, one can think about that function space as built in a very complicated way out of all these pieces that we've written down.
yeah, that's right. I should comment, this will come up later, just while it's on the board. So if you want to understand functions on SL2R, so as I've written them down, these are all functions on SL2R. Maybe if you want to be slightly more analytic, you might say L2 functions on SL2R, and these are not all L2 functions. So the ones that are kind of close enough to being L2 functions to appear somehow in that representation, when you write down this sort of Fourier integral theory, are these ones, these discrete series things, trivial representation. And, well, no, sorry, they're not the trivial representation. That's not L2 on SL2R. And not these ones. These ones with lambda not 0 don't appear. Only the imaginary ones appear. So this is already something. Turns out these ones that appear inside the function space, we do understand. And this is kind of central. So these are called tempered. Those words will appear a lot. But then there's these other ones that also sort of sneak in, which are sort of some slightly laxer sense of functions.
I mean, another weird thing is that, say, for semi-simple groups, this is one of the reasons why we are studying semi-simple groups, that any unitary representation is expressible as a direct integral of unitary reducible representation. But there are examples of Lie groups where you take a unitary representation and there are two different positions in a direct integral with disjoint supports. So the notion of irreducible representation is good in this case, but in general, they're just, it's completely contrary to our intuition.
Yeah.
Okay, so the basic question is saying, given like just from the initial setup, you say look at L2 functions of the group. That would be unitary, trying to decompose that.
Yeah.
And you can do that obviously for any real form. It doesn't get everything, but the things that show up there are understood in general.
Yes, that's right. So this this thing of decomposing the functions has a name. Usually the name Fancherel form that is thrown around. It's some way in that story. So this I think was done by Harish-Chandra for these groups. And so it turns out those representations that appear, yes, are very well understood. And then the rest is just that there's these other ones that are mysterious and somehow that's where the hard thing is. So a lot of this game, which I was trying to explain, involves reducing questions about general representations to something about tempered things, which we understand.
But the other stage, the group of the children,
Yes, that's right.
that's also say.
Yes.
Maybe we can discuss that at the end, that's very important. Let's have a discussion about that.
So now let me get into this Harishchandra one. So this is, in some, well, this in my mind is why the fact that this theory works is why all of our sort of intuitions from algebra actually work in this setting, because you can actually relate this whole analytic story to some algebraic story. So I'm going to just make some choice. So I fix my real group in a real form. I'm going to fix just some maximal compact. And so I can always take a maximal compact subgroup, which is unique up to conjugation by some general theory. And then let me, just because I will somehow, like probably a few of the students, maybe, I don't know, I don't always like thinking about Lie groups. I quite like thinking about algebraic groups. So let me complexify this. So if I don't have a sub R, I have a complex thing. So this is just some reductive subgroup inside my complex reductive group. Okay, and so what Harishchandra sort of does is he defines some class of sort of nice representations with respect to this. So define V, some GR module, to be admissible if all of the irreducible representations of this compact group that we understand appear finitely many times. So the multiplicity space of every irreducible of K is finite. So I might write K hat sometimes, but I've got a reductive group for just the the usual finite dimensional irreducible representations, which is the unitary dual of this KR. Okay. So now if you have one of these admissible things, you can do the following trick. And I'm probably going to regret rubbing out my example, but it's done now. So what I can do is I can define the set. So I can look at this subspace inside my my representation, consisting of finite action vectors on whom the action of this compact group is finite. This is just a set of vectors V and V such that the dimension of the span of the KR orbit is less than infinity. And this is just another way of writing this. It's just always the sort of finite direct sum of all of these multiplicity spaces. So if you like, well, how you should think, and I'll give you this in our principal series example in a moment, this vector space, this this bold V, this is because it's somehow given by the kind of representation theory of compact groups, harmonic analysis for these things. This is just given by some kind of infinite series whose terms kind of correspond to each irreducible representation of KR. So the basic example is Fourier series of this flavor. And so what this V does is you just don't take infinite sums. So this infinite sums are painful, so don't do it, just take finite sums. That gives you some kind of vector space inside this topological thing, which is dense. This is dense. And so this thing is called the Harishchandra module. So V is called the Harishchandra module. And it is it's a GK module. You've ever seen these words, this thing GK module shows up a lot in life. So what this means is it has an action of K, a group, what it obviously does, how I defined it, and an action of the Lie algebra. So here G is the Lie algebra of G. which is the complexification of the Lie algebra of the real group. So the idea is the real group no longer acts on this because somehow it wants to move things to infinite sums, but kind of sort of infinitesimally it still acts. So you can still kind of differentiate that action, get a well-defined Lie algebra action on this P. And so when I wrote down this sort of classification of irreducible representations of SL2R, really that's correct if you say classifications of irreducible Harish-Chandra modules. So this kind of throws away all this sort of issue of which kind of functions do you take. So maybe because I'm running out of time, will not write down the principal series Harish-Chandra module. Exercise, do it, and realize that this decomposition is Fourier series on a circle in that case, with some extra SL2 kind of decorations going to this G.
Google, I feel like it is worth going 5 minutes over to see this example because it's so
Okay.
important.
Is it worth going 10 minutes over? Okay, no, I will do the example. All right, so if I take this principal series thing, so this is GR as SL2 again. So if I take these principal series, let me do it for the plus, and the minus is very similar. So I'll do it slightly sketchily. So take one of these functions. Now, sitting inside here, I should say, by the way, let me take my KR, so I could choose it. Take the obvious once you've thought about this for a little while. Maximal compact inside here, which is SO2. So this is a circle. That's where the circle comes from in the story. So what I can do is I can take these functions, these are functions on SL2 of R, let me just restrict them to K. So if I restrict to KR, and whatever kind of reasonable functions I take, the way that this transformation rule is enough to actually recover the function. So this actually gives you an isomorphism of vector spaces onto functions from SO2R. You can see SO2R is just a fancy name for a circle of whatever class I was interested in, such that, and then there's a little bit left. So the -1, basically the idea is this K and this B are sort of transverse inside the group. There's one little bit of intersection, which is the -1. So the -1, 0, 0, -1 is in both of them. And so you have to make this, because of how this -1 acted here, the functions that you get will have to be even in this obvious sense. And I just call this K instead of a Z. So I'm getting even functions on a circle, which is functions on some quotient circle. Fine. Okay. So this is it as a K representation. So if I just ignore the G action. And so this is some, whatever this function space is, this is some class of Fourier series. And all the ambiguity was about which class of Fourier, which sort of infinite sums I allow in this picture. And so this Harish-Chandra module, whatever class of Fourier series you take, you'll just get finite sort of Fourier polynomials. The Harish-Chandra module is V. This is my bulk V. This is the direct sum over, well, let me write it like this. So there's some evenness condition because of this evenness. Let me say it has a basis given by these integers, where the Vn, so Vn of, let's see, what does an orthogonal matrix look like? That's an orthogonal 2 by 2 matrix, so base squared plus b squared is 1. So let me take, just to be definite, that function. And so this is Fourier series space. So the fact that this V was a completion of the space is the theory of Fourier series. Okay, and now I don't want to do it on the board because this is maybe, it may be easier to see from other perspectives. So work out the SL2 action. I recommend actually doing this exercise if you've never seen this before. but one thing you might do when you try and do this exercise is realize that it maybe is more convenient to think that your H is the generator of this maximal torus, not the usual one. So that this is an eigenspace decomposition. So that this is weight space for some Cartan decomposition of SL2, maybe not the one that you usually use. So let me, the remaining 5 + 5 minutes, say a little bit, but I think Dragon will explain this. We'll explain this properly. When I say like the specification, I mean the Valence and Bernstein version of it.
I'm sure that was so shy, but I'll try.
At least in a, we'll see, anyway.
And properly, I would.
To the extent that I'm explaining anything. Okay. So let me just give you a very sketchy picture of this thing. So what I really want to talk about is this algorithm. And so I need a little bit of this the shape of this classification. So it turns out, oh, actually, I left out the most important thing. Let me just squeeze it in here. So this big theorem of Parashchandra is that the unitary representations of GR, this whole procedure, so first of all the irreducible unitary representations of GR are admissible, so you can do this to them. And in fact, that procedure is a bijection. So the irreducible unitary GR mods are in bijection with irreducible unitary GK mods. Where unitary, I'll just say it in words, means you have invariant form for the natural real, the algebra here, and the real form of the compact group that's positive definite. So whatever, think about what sort of structure you would expect to find, and that's what you find. Okay, so in other words, you can, this problem is completely algebraic, a posteriori after you've done all the work. So and that's why all of our algebraic intuition actually works in this case. It's actually an algebraic problem. Okay, so this is a little preview. So now is the one place where some D modules will appear, although very, very sketchily. So we're interested in these GK modules. So if I forget about the K, these are the algebra modules. So hopefully, I think we've now done enough of this localization, this D modules course, that you know that with some meaning of double arrow, these are the same thing as some twisted D modules on G mod B. The flag variety of my complex group. So it's a nice complex flag variety. And then this K is just imposes some equivariance condition on these. So K, from this geometric perspective, really all that, after all of this sort of analytic nonsense, what you're really interested in is studying some interesting subgroup of G acting on G mod B. So we'll decompose it into some orbits. And then you're sort of studying D modules sort of that make sense on those orbits. So kind of from the kind of general geometric picture, so the irreducibles are some sort of IC sheaves of K orbits. So they're classified by a K orbit. I need a lambda. So this is going to be my twisting. Okay, I won't define Gothic H. Okay, you can use your imagination. And some local system. So the correct adjectives are irreducible, K equivariant, lambda twisted local system on here. So for always abbreviated local system. Okay, so this so you have some parameters. You come with some suborbit and some local system, and then this general theory of D modules. Let me write J from Q into G mod B for the inclusion. So the general theory of D modules gives you some modules on G mod B. So there's two ways of pushing forward in the world of D modules. When you have some locally closed immersion like this, you can shriek push forward and star push forward. Okay, so these are some things. These are sum operations, and they're sort of left and right adjoints in some sense to something. And so because they're constructed in some left and right adjoint way, you have naturally a map from one to the other. So you have this sort of canonical thing coming from D-module theory. And so you can just take the image of this. So that is intermediate extension, aka intersection cohomology in some guise. So these are the irreducibles. But somehow these irreducibles kind of jump, as you maybe saw in the principal series case. What's natural are these modules. By the way, the principal series was one of these in disguise. What's natural are these modules, and there's some map, and then it's sort of the irreducible the socle, I guess, of this one, and the co-socle of this one are the irreducibles. And so those will jump when these become reducible. But these things vary in a nice family. So that's sort of how you should think. So these, by the way, I'm calling this the Langlands classification because, well, arguably either Harshchandra or Langlands were the first people to do this, not in this way.
Explain that, but I mean, I'm not sure if I can say any details about relating this to actually the Langlands technique.
That's fine. This is the version that we will use
Yeah,
for
okay.
everyone. I just wanted to make as a comment. So you can do this algebraically. So it was originally done that way. But since this is a D-module thing, this is what we're doing. It's a nice kind of modern, with a hammer way of doing this. Okay. So I'll just sort of say some facts verbally about this. So as I said, these two things in this map, these sort of vary nicely as you vary this continuous parameter. So the continuous parameter is lambda here. Everything else is just some sort of once you fix lambda, there's finitely many other things you can choose. So as you vary lambda in whatever space you're allowed to vary it, which depends on the orbit, these two things kind of vary continuously, and this jumps. For generic lambda in whatever space it's allowed to live, this map is an isomorphism, so they're all just irreducible. So again, we saw that in the principal series. And then interesting things happen when they become reducible. And the other thing which I will say, which is a slight lie, but was almost true. So inside each of these continuous families that you have attached to the orbit of the local system, you can always deform this thing so that it becomes tempered. So one of these representations that we understand. So in particular, that we know are unitary, sort of key. It's a slight lie. You have to mumble that into defining functors or some things. So, but more morally, it's true. So let me just give you the idea behind this algorithm. So this idea, I think, goes back to Vogel. So you can at least find, I don't know if it, maybe exactly when it goes back to, but you can find it very explicitly in a paper of Vogel from, an annals paper of Vogel from 1984, I think. So this is how old this idea is. So the idea is you want to compute, the signature of your invariant form on one of these irreducibles. And so what you should do is two things. You should deform it to a tempered thing. So you deform your parameter so that it becomes tempered, and then you know the signature. And then you have to keep track of what happened as you did that. Keep track of changes. And what you see from this picture is also on these standard modules, on these modules, this signature is of course going to be constant when this thing is irreducible. Signature can kind of only jump if it becomes degenerate. So when it becomes degenerate, when it becomes reducible, this form will become degenerate, and then the signature will change. And you have to kind of somehow keep track of those changes. And so roughly you can write some sort of in principle formula. So you want to know the signature kind of above a wall that you cross where things become reducible. And so this is going to be the signature below the wall plus some corrections. And so these corrections are given in terms of the same problem for lower dimensional orbits. So somehow you could write this in terms of forms on other sort of composition factors of this thing. So, and those things will all actually come from lower dimensional orbits. And so you can then iterate that to compute those correction terms. And so you do this, you get some sort of huge recursive algorithm, and that computes the signature. Now I said this was, so this idea was from the 1980s. There are problems in implementing this if you actually want to do it. So one problem is how on earth do you do this in practice? So how do you write these formulas? And so the solution to this, it turns out, is some kind of, so how do you do this? This is some kind of cut-down-listing theory plus a bit extra. And so eventually I figured out how to do this. And so the other issue, which really you have to solve before you start that last one, let me just say this and then I'll finish. So the other issue is you have to actually do this in practice, you really have to be able to normalize the forms because of this recursive thing. If you want to kind of plug in, you need to know, you know, did your representation appear in this correction term appear with your favorite version of the Hermitian form, or mine is your favorite one? So to answer that question, you have to have a favorite one. And it turns out that's kind of hard to do for these GR invariant forms. So it's kind of hard. So for example, if you look at the standard representation of SL2R, SL2R acts in C2. I challenge you to pick a canonical Hermitian form on this one, invariant Hermitian form on this representation. There's two, which have sort of, you know, if you look at the two weight spaces with respect to some choice of torus, one of them will have positive signature and the other one will have negative signature. But how on earth are you going to pick which one is going to have which? They're sort of these two weight spaces sort of look the same, they're conjugate on the bar group as well. So the solution to this, let me fix some maximal compact inside G. Okay. And then we choose it so that it contains the maximal compact inside GR. Okay. And so that gives you some the algebra U, lowercase UR, which is another real form, so compact real form of your Lie algebra G. And so the solution is, so don't look at these GR invariant forms, look at the UR invariant forms. So for these, you can normalize. So again, I'll say it in words, I should stop. So what you can do is you can normalize these. Turned out inside your representation, you always have something called some minimal K types. There's some sort of pieces of the K representation that are in some sense as small as possible. And it turns out that UR invariant forms always have the same signature on all of these minimal K types. So you can declare that to be positive and you've chosen a canonical form. So for SL2, for this example, there are two minimal K types, the two weight spaces, and they have opposite signatures for the GR form. So that's why you kind of wouldn't normalize. So these UR invariant forms you can normalize, and then it's possible to pass from the UR to the GR invariant forms sort of at the end of this procedure. So let me stop there and I'll explain that procedure either tomorrow or the day after.
This is really well. You've got a survey from the day load rate to the negative extension and then include them.
Yes.
Do people study like is there an indecomposable object from J load straight to J load at start? I'm not asking where you have an inclusion.
So inclusion and a surjection.
Yeah.
Yes. I mean, this is something Kari thought about a lot about in his life, I think. Yeah, so there are these objects. So you can, so one thing you can do you have to be slightly careful about what category you do this in, but you can certainly do this something called the maximal extension, which has this shape, certainly has those maps. So valence is maximal extension, which actually plays a role in this whole story. You can also try and play this, do these tilting. Of course, when you look at n orbits on G mod B, there are these tilting objects that people like to study. I guess these are also in that larger category. Whether you have a general tilting story here, I'm not. No, I guess you don't. Yeah. So anyway, there is something, but maybe the words are slightly different than maybe some other contexts.
And maybe it's important to say maximal extension really needs that the boundary be cut out by a function.
Yes. So this is exactly. So this is, I'll say, elaborate on that because it's kind of central to everything. Yeah. So one thing that you have for these orbits, so I kind of blithely wrote down this J shriek and J star. Now, if you actually look up the definitions of these things, these are some functors between derived categories. So I asserted that they were D modules. And the reason is because the boundaries of these orbits are actually divisors, so they're affinely embedded. You can still, of course, make this definition with the just only take the zeroth homology piece, but it's sort of useful that these are actually derived. These are underived. To then do this, maximal extension thing, you need to actually have an equation for that boundary. So there is an equation for these boundaries, it just lives in a line bundle. So the words that one say, maybe you can say it as you can get one way to say it is you can get a genuine D module on G mod N instead of on G mod B, which is what this maximal extension is. And then this will have this property of being monodromic, so it almost looks like a twisted D module, but slightly more. So another point is that this, when you do this Valence and Bernstein story, you have some center of the universal enveloping algebra acting by a character. This monodromic thing, you need to allow generalized characters, so generalized eigenvalues. But yeah, somehow this point that these orbits are cut out, their boundaries are cut out by equations is essential. This is sort of one of the essential bits of geometry that makes what I will talk about in some of the other days work. But yeah, this forces you to pass to these monodromic settings.
Maybe so. Carrie brought up the fact that one is very interested in representations that occur in other function spaces. Would you be able to briefly comment on that?
Well, maybe Kari is the best. Briefly comment on that. I mean,
so for example, in number theory, if you take SL2 mod gamma and look at functions on that, then there's, for example, Ramanujan conjecture, which says that one of the things that you wrote down, only so you have the easy unitary representations, and then you have the tricky ones, and then what is Ramanujan conjecture? Something like it only comes up to a quarter or something. So like very specific Iraq show up in G mod gamma for a common subgroup. And this is, it's like Ramanujan conjecture, so it would imply things in number theory that people would be very happy to prove. And so also just a historical remark. You said kind of motivation is like differential geometry. I take a space, I take algebra functions, I get a unitary representation. And then you also said quantum mechanics. But my understanding is that, but like my understanding may or may not be.
my understanding of the history may also be wrong.
So is it so Weil explained representation theory of compact Lie groups, and the connection with quantum mechanics was realized, and people were very happy. This is the story of compact Lie groups. And Dirac said we should also be able to generalize. We should also be able to clarify general relativity by looking at Iraqs, for example, of the Lorentz group.
Yeah.
And Dirac wrote down a classification which Harishchandra didn't believe. He didn't believe the proof of, and reproved, hence became a mathematician. But that essentially, like the representation theory of non-compact real groups kind of has never been important in physics.
It could be true.
Like
I don't
my
know.
understanding, like there's some line in Langlands where it says, my impression is that this has never actually been important in physics, but it turns out to be extremely important in number theory and things like that. So that was just.
Yeah, that's possibly true. I mean, yes, probably the group that you're interested in are the Lorentz group, which we understand. It's not such a complicated group.
I mean, it's important, but depends what kind of physicist you are. There are these people who are saying studying dynamical groups of certain systems, and there you get various non-compact groups which explain your finer structure, say, of energy levels in your system. For example, you can, if I remember correctly, if you want scattering theory for hydrogen atom, then you can interpret this using some low dimensional non-compact group. I mean, SO4, I think, explains the bound states, but for scattering, it's probably SO3 something like that. But not like standard Lorentz group, but completely different. So it depends.
Mhm.
What do you mean?